Okay, so hi everyone, welcome to today's SciML webinar. Today we have Justin Beroz giving a talk and Varun Shankar as our session chair. So Dr. Varun Shankar recently finished his PhD in mechanical engineering at CMU, advised by Professor Venkat Viswanathan. His PhD research focused on leveraging machine learning and AI to improve the accuracy and efficiency of computational fluid dynamics methods. He's now working on a new venture called Physics Inverted Materials, which aims to leverage scientific machine learning principles to improve methods in computational materials design. With that, I'll hand it to you, Varun.
Thanks for that introduction, Keith, and thanks for the invitation. It's good to be back here this time as a session chair. I'm really looking forward to today's talk. I think our speaker has some really interesting insights to share from his work on fluid modeling. So today's speaker is Justin Beroz. He received a bachelor's through PhD in mechanical engineering, focused on precision mechanical design. He's currently wrapping up a second PhD in theoretical physics at MIT, where he's advised by Professor John Bush in the Applied Math Department. Justin recently received the John Jarb Seed Fund for Science Innovation for his work on modeling turbulent fluid flows, and is commercializing a new computational fluid dynamics solver through his company, ReynKo Inc, which is supported by the Activate Fellowship in New York. So with that, I'll hand it off to you, Justin. Thanks.
Great, thanks, Varun. So let me go ahead and share the screen, and we'll just jump in. And please, anyone at any point in time, if you have questions, please stop me and ask. So let's see. Now I need to figure out how to share the screen here. Okay, can everybody see this?
Yep.
Okay, so today what I'm going to talk about.
I guess right now we're seeing the displays. If you
right?
swap the two, we're seeing the sort of the second screen, not the main.
Oh, okay. Let's see here. Let me try this again.
If you share again the way you had shared before, and then swap the screens. Yeah, that's good.
This is good?
Yeah.
All right, awesome. Okay, so today what I'm going to talk about is a model I've been working on for turbulent fluid flows. So I'm just going to jump in with a little bit of an introduction, and then I'll get the outline. So first, let me start by asking the question, what is the turbulence problem? So the turbulence problem is considered the longest running unsolved problem in classical physics. And it refers to how do we mathematically model the chaotic fluctuating behavior that's typically exhibited by a flow. So anytime you have a flow that's moving at a high Reynolds number, you have fast speed, it tends to destabilize and create these complicated fluctuating swirling patterns. So what you're looking at right here is a picture of what's considered quiescent room air. So this is room air that's considered stationary. But however, if you put a little smoke and a green laser sheet through it, then you see that it's by no means stationary, and there's all these fluctuating patterns that are happening within. So you can see these also tend to be on many different length scales. So you have like bigger ones, and within the bigger ones, you see smaller ones and smaller ones and smaller ones. So generally speaking, this is what we mean when we talk about turbulence. So specifically, what are we talking about when we say the quote turbulence problem? So the simplest example of solving this problem is the following. We start with the incompressible Navier-Stokes equation. And just as a quick review, Navier-Stokes is really nothing more than Newton's second law. So you have on the left-hand side, the time derivative of velocity with its acceleration. And on the right-hand side, you have the sum of forces. So there can be a pressure gradient, viscous drag. And then there's a nonlinear term here, which corresponds to the convection of the fluid itself. And F is just some arbitrary body force that may also be applied. So really the statement of the problem is to start with this and somehow manipulate this into a form that's fruitful for talking about these turbulent fluid motions. And what will become pretty painfully obviously clear soon enough is that it's really a nonlinear term that causes all the trouble here. So brief outline. One, I'm going to go through a couple relevant historical contexts. Then number two, I'm going to get into my own model framework. And then we'll start getting into some fun stuff. So we'll do some scaling and look at the energy spectrum, which I'll derive. And then finally, I'll talk about a specific example, which is turbulence in a cube. So first, let's start with the original picture of turbulence here. And this comes from Reynolds back in the late 1800s. And his picture was to say, okay, let's take this volumetric domain of a fluid that's highly turbulent, and how do we start at square one to sort of make sense of what this is? And what Reynolds said was, okay, let me first do a time average over the whole flow. So if you do that, you can produce some regular looking field, and that's notated here by the B bar. And then on top of that, there's some sort of fluctuation about the mean, which is the delta V. So with this decomposition, if you now plug it back into Navier-Stokes and time average the whole thing again, you get something that's called the Reynolds average Navier-Stokes equation. And what you see here is that it looks basically the same. The only difference is that we've picked up an additional nonlinear term, this one having to do with the fluctuating components. Now the problem here is that when we do this decomposition, you'll notice that we have the same three equations of motion, right? So we're looking at a fluid flow in three-dimensional space. So there's an equation for each coordinate direction. However, now that we have the mean and the fluctuating part, we have 6 vector components, 3 for the mean and 3 for the fluctuating part. And so this is what's referred to as the closure problem, and we don't get any additional equations of motion. So somehow, in order to have a closed system of equations to actually solve, you need to somehow, within this framework, relate the fluctuating part to the mean. And this is what's called a closure equation. And depending on the context, these go by many different names: eddy viscosity models. If you're doing computational fluid dynamics, these are like K epsilon, K omega. There's more that are more modern, that are more complicated and have more terms in it. But really the essence of it is trying to find a relationship between the mean and the fluctuation. Now, this is something that I spent quite a bit of time thinking about, because it turns out that no matter how you manipulate this Navier-Stokes equation, you can never really get this closure issue to go away. And I was asking myself, well, why is this? Why can you never get rid of it? And what I came to understand is that the problem really starts with the decomposition up in the beginning. When you break the flow down into a mean and a fluctuating part, the relationship between the mean and fluctuating is not one-to-one. And so you will always run into trouble if you're trying to write a functional relationship between those two. And the easiest way to see this is that you can imagine there's all kinds of spectra of turbulent fluctuations I can cook up, where if I do the time average of the whole thing, I get the same mean, right? So I basically taking the thing that I don't know about fluids, which is this relationship, and I put it right at center stage. And so this is what sort of motivated me to think, maybe there's a different way than going down this this particular velocity decomposition to make sense of this. Okay, so we'll jump forward in time a little bit. The other important thing I want to mention is Kolmogorov's picture of turbulence. This is perhaps like the most famous and biggest success story in turbulent fluid modeling to date. And what Kolmogorov said, this is essentially a phenomenological argument. He said, okay, let's imagine we have a flow that's turbulent, and it's very turbulent over many orders of magnitude for these turbulent fluctuations. Well, in this case, we can essentially break the flow down into 3 different stages. All right, I'm going to check the chat here. Okay, we're still good to go here? Yeah. Okay. Okay, so you take this flow and you break it down to 3 regimes, essentially. So one is on the smallest length scales, you can have viscosity kick in and dissipate the energy as heat, and that's called the dissipation range. On the largest size, you will have an influence of the domain geometry itself. So this is sort of like geometry dependent at these largest scales. And so you can imagine if you're sort of forcing a flow, it's at these largest scales where the energy comes in, and then it will essentially on these length scales, like the flow is basically inviscid. So the energy you're pumping in has to somehow get down to these smallest scales in order to be dissipated. So this is what's called the energy cascade, where it goes from larger to smaller and smaller length scales, and eventually you hit viscosity, you can dissipate the energy. Now, within an intermediate regime, so imagine now where several length scales are removed from the production range at the largest scales, and we're also removed from dissipation. There's this region in which the energy is essentially just translating down from a larger to a smaller length scale. And in this picture, there's a reduced set of parameters to describe the fluid flow. And in particular, the only thing we have is the wave number k, and the corresponding amplitude of velocity fluctuations. So from here, we can do some dimensional analysis. And there's two things we can come up with. So first is something that has units of energy dissipation. So this is like energy change per unit time. And then we can put together an energy spectrum. So this is within a certain value of k, what is the amount of turbulent energy that's at that particular wavelength. And what you see is that just by dimensional analysis, you get this famous scaling, which is k to the minus 5/3. And this is the Kolmogorov scaling here. And if you have a sufficiently turbulent flow, which shown in the bottom right, this is experiments of turbulent air flowing in a pipe, you see that this scaling does emerge. And in fact, this is one of the things that computational people look for when you're trying to validate your simulation, right? So if the flow is sufficiently turbulent, you should see the scaling arise. Now, let's connect this back to Navier-Stokes. So let's take the Navier-Stokes equation here and dot the whole thing with velocity again. So if we do this, we notice that when we're looking at that energy dissipation rate term, there's only one term in this equation that has the right units, and that's the nonlinear convective term. You see, that's where you get a v cubed, and then you have a gradient, and so that gives you the k. So in a very real sense, like this whole energy cascade, the interaction of energy exchange between all these different length scales is all happening through this nonlinear term. And so this is the one we really need to contend with to understand what's going on. Okay, so now this is up to present. We're going to get into the work I've been doing. And what I said was, okay, let's start with a little bit different velocity decomposition. And so the picture is basically this. You're going to start by turning all the turbulent fluctuations off and just finding the laminar flow through a particular domain. Okay, and that's this capital U. And essentially what we're going to do is take this capital U and treat that as part of the domain definition itself. So you have the structure of the domain and this laminar flow through. And then what we're going to do is look at any sort of disturbance of the velocity field superimposed on top. And that's this little u. And so we get a similar decomposition for the pressure fields. And now if we plug this decomposition into Navier-Stokes, we get something again that looks kind of similar, except we pick up a couple extra terms. In this case, we pick up two linear terms in little u. And these have to do with the energy exchange that's happening with the base flow, which is the big U again. So the other definition of interest here is the kinetic energy density per unit mass. So this is just taking the inner product of little u together. And this is a measure of the turbulent energy density field throughout the domain. And of course, we can take the time derivative as shown here. And so what we're going to do, the only other ingredient we need is we need to take the full flow field, and we're going to do a spectral decomposition of it. So imagine, there's a number of different orthogonal function fields, which we can, basically superimpose on top of each other, and the sum of all of those is going to be the complete flow field. So that's this decomposition to the sum over k. And by definition, what we're saying is that there's some sort of normalized version of this velocity field, and then there can be some amplitude on it. So the way we actually calculate this is we take each one of these, I call them basis functions, and we take the total flow and we project it on. And what we really need to talk about orthogonal functions here is we need some sort of metric of orthogonality. And this is a pretty crucial part. And so the metric here is that if you take two of these fields, take the inner product of them together, and then volume average the whole thing. And so volume average is represented by these brackets. Then this will give you a number. And you can talk about whether this number is 0 or 1. And it's in this sense that we talk about orthogonality between these different fields within the flow. Okay, so with all these components, basically from here, you turn the mathematical crank and you substitute them all in together. So you can say, okay, we have the kinetic energy here. Here's the equation of motion, the time derivative for the kinetic energy. And for the time derivative of u, we can plug in what we have for Navier-Stokes here, and then also keep in mind that we're going to do this velocity decomposition, and we're going to plug that in there as well. So we just turn the crank. It's a pretty long mathematical exercise, but the result is this at the end of the day. So we end up with something here, and notice that everything here, this is the kinetic energy equation of motion for each one of these fluctuating field components. Okay, now there's some things that are not interesting that I'm not going to talk about here. So, one is you can have a forcing from F, and then all these J terms, these are just fluxes that are happening across the surface. For instance, if you have a rigid boundaries, then these essentially all go away. So we're not going to worry about those. The really important thing that I want to focus on today is what's happening within the interior volume of the flow. And that's represented by the first term here, which has a sum over K prime. And so here we have two things that pop out. One is an H operator, and the other one is this S operator. Now, the H operator, this maps to all of the linear terms in the Navier-Stokes equation. And specifically what we have is we have a symmetric component that's coming from the energy exchange of base flow. And then we have a symmetric component that has to do with viscous dissipation. Now, part of the reason of putting this into the kinetic energy framework is that this symmetrizes all the linear terms in this sense. So, ultimately, we're going to be talking about eigenstates, and we're talking about the eigenstates of this particular symmetric operator. Now, the new part here is the nonlinear operator, and this maps to the nonlinear term in Navier-Stokes. And this guy is anti-symmetric. So it's essentially a sum of different terms, which you can think of them. This capital omega is essentially like a vorticity tensor in a sense. And so essentially what this is doing is this is telling you how the energy is exchanging between these different K states. Right, so this guy's always anti-symmetric, so you're basically pulling energy out of one, you're sticking it into another. So this is the basic form, and of course this is sort of all close here, and we can clean up the notation a little bit. So first we notice in the first box up here, once we do the inner products and take the volume averages, these equations here are really, we're talking about a bunch of scalars, right? So we can put this in a pretty explicit matrix representation. So first, just writing explicitly as scalars, you get the kinetic energy form. If you chain roll out this time derivative on the left, you'll notice that there's a UK sub I that we can get rid of, and then we end up with this velocity form, and this is really looking like a matrix equation now. Now here, this subscript I represents that we're taking the eigenvalues. So we take this H operator. And there's particular eigenstates of fluctuation where we get the same thing back multiplied by this guy H. These nonlinear terms here are the matrix elements that look like this. Okay, so putting this explicitly into a matrix representation, this is what we have. So this vector U represents the amplitude of each one of these eigenstates of fluctuation within the flow when we put them all in a vector, and then we can range them such that we basically have like an ordered list going all the way down. And so within this eigenstate representation, this will diagonalize the H matrix, and then the S matrix will be anti-symmetric, so you have terms that that look as shown. And so I want to emphasize that from this point, this is where you can really do calculations, right? These are really just numbers in a matrix, and you can, just basically do the matrix multiplication to see the evolution of this turbulent system. The key crucial point is that the math we just went through tells us that each one of these components corresponds to a specific flow field within the domain. Now, there's sort of two pictures we can take on what the turbulent exchange looks like. So the first one, if we're thinking about in terms of linear eigenstates, the picture in the top right, I find pretty helpful. So this is like a configuration space representation of the system. So you can imagine a coordinate system. This is in principle, sort of like an infinite dimensional coordinate system. So we're really sort of talking about a Hilbert space here, where along each coordinate direction, that will coincide with one of these linear eigenstates that diagonalizes the H matrix. And so there will be essentially a vector that's pointing along each one of these with a certain magnitude, and the vector addition of all of those is giving you the state of the overall flow in this configuration space. So as the flow evolves over time, this point is basically moving around. And this will correspond to basically an exchange of amplitudes between each one of these different coordinate directions. So this is the first picture, all right, where we can think of energy being pulled out of one and stuck into another. So you can imagine like the little vectors in blue changing length. An equivalent picture is to take this whole thing, the H plus S, and treat that as one matrix. And then we look for the eigenstates of that. Now, in this case, because H is anti-symmetric, we will get eigenstates, and I call these the nonlinear eigenstates. The difference here is that because this matrix isn't like generally symmetric or anti-symmetric, we're really going to get eigenstates that are no longer orthogonal to each other. So an equivalent picture, and this is what I'm showing in the green, is essentially the following. As the nonlinear exchangers start to kick in and cascade down within the length scales in this flow, one way to think about it is that these nonlinear eigenstates start aligned with the linear eigenstates, and then as the turbulent exchanges sort of ramp up, they will not only change amplitude, but they also start to move, and they'll move away from the coordinate system axes. And so now the inner products between these different nonlinear eigenstates is a different but equivalent measure of the energy exchange between different length scales. Okay, so yes.
A couple quick questions. Thanks for that outline. So can you help me sort of understand what makes this decomposition distinct from the Reynolds decomposition? I know you said like sort of the base flow is the laminar flow.
Yep.
I guess if you have any more sort of explanation of what makes this different.
Yeah, well, essentially it's what you said. So, okay, so the laminar base flow is something that's unambiguous, right? So for instance, just think of it as the Stokes flow through the domain. So this is something that will always be satisfied, and it's a sort of unambiguous base flow that's happening through the domain. So this is different than the mean flow in the Reynolds decomposition, because you have all these turbulent fluctuations, and you do a time average over that whole thing. And in that case, what you're getting is not the same as the laminar base flow, right? Because all these turbulent fluctuations change whatever this sort of regularized field looks like. And so there, you have an intimate sort of relationship between the mean and fluctuating part. Whereas here, there's really no ambiguity. It's just the Stokes flow essentially, plus any disturbance that's happening on top. So you essentially get to skirt around the turbulence problem because of this difference in the decomposition.
Makes sense. And so how do you compute these like basis functions, and how many like modes, or how many basis functions do you need?
Yeah. So I'll couch the question of how you actually calculate these so when I get to turbulence in a box, because I'll go through this explicitly. As far as how many you need, it depends on the Reynolds number of the flow. So in principle, you can keep this list going down, to as large of a wave number as you like, and so in this sense, it's sort of like this linear velocity eigenstate equation of motion here. What this really is a nonlinear Schrodinger equation, right? And like the H is really sort of like the Hermitian Hamiltonian of the system. In practice, however, as you get to smaller and smaller length scales, the system begins to normalize. So the S matrix here, these have an additional scaling with the amplitude of the velocity fluctuations, and as you get smaller and smaller, these get damped out. So there's some point where you can essentially cut things, where you say, okay, from here downwards, the whole system is essentially orthogonal, and you don't have these nonlinear exchanges happening anymore.
Gotcha. Thanks.
All right. Okay, so we've now gotten through the painful math, so let's get on to some of the fun stuff. So we'll start with some scaling. And where we're going here is we're going to find the steady state turbulent energy spectrum, and we'll find that this compares nicely with experiments. So what I have written at the top here, this is again this kinetic energy equation of motion from before. And in steady state, what we're going to do is say, okay, well, the time derivative is essentially 0. We'll take the simplest case and we won't worry about any of these external forcings. So Q goes away. So we're basically just left with the H and the S matrix. So that's what's shown on the first line. And on the second one, I'm putting in the scaling for these terms. So for H, remember there's two components. One has to do with the rate of strain tensor of the base flow. And so that will have a scaling that goes with the amplitude of the base flow, capital U, and then there will be some characteristic gradient, which is the KU. And this alpha out front, just think about this, like if you were to calculate this exactly, you get some number out front, and that's what this represents. So, I mean, this is really a scaling. And, as long as you're finding these these characteristic values appropriately, then these numbers out front will be presumably something like order 1. So you have this guy, and then you also have viscosity. And so the energy dissipation for viscosity is going to go as k squared. That comes from the Laplacian operator. And then you have the kinetic viscosity term, and again, another coefficient out front. And then similar scaling for the S matrix here. So you see that we get 2 U's here, and there's another U that's wrapped up into the S itself. And so we'll get something that's of this form summed over these k primes. So this is the thing we need to sort of contend with and figure out how to simplify this. And one nice way to do this is to imagine, okay, we have a very turbulent flow, over many, many orders of magnitude of these turbulent fluctuations. And so if that's the case, we're basically summing over this k prime over many states. So we can do a continuum approximation where we basically turn this sum into an integral. And the way we do this is we say, okay, let's integrate over states starting at k. And then the integration is over k prime. And the way we're going to do the integration is we're going to start widening the window around k. And the width of that window is called this delta k. And so as we sort of integrate and increase the limits more and more, that way of doing the integration, we can also have this correspond to a Taylor series approximation in terms of this delta k. So that's what we're seeing here, and I've done the approximation with the first 2 terms. So we get something that's order 0 and order 1. Now the order 1 term you can see here, we have 2 terms of equal amplitude but opposite sign. They cancel each other. So that term's 0. However, these components themselves, we can identify that as being the energy dissipation that's happening at wave number k. And so the idea is basically this, like this is the energy that's, for instance, within the spectrum, it's passing through this state UK, and this is the amplitude of the energy that's, same coming in as going out. Now, as we start to include these nonlinear interactions, we get something that's proportional to this delta k prime. And through a more complicated exercise I won't get into, like keeping track of like the energy going to one state, and then from that one to another and another, you find out that this k has a relatively simple scaling, and you have something that's basically approximate to k itself, and you have some coefficient out front. And doing the detailed math, you find that this is a number that's somewhere around 3. So putting all this together, we now have a governing equation here. And again, I'm really going for scaling. So, as far as these like order 1 coefficients out front, I'm just gonna, set them all to some, sort of characteristic approximate constant value. And we now have this equation to work with here. So with this governing equation, there's a couple things we can do. So first, we're going to simplify it by just non-dimensionalizing things. So we have some largest wavelength, largest wavelength, smallest k number, which is on the size of the domain itself, which is this capital L. We have a characteristic velocity amplitude, and then we have this thing called tau. And putting all these in, we get a simplified looking equation like this. And from here, we have something we can integrate. So we integrate this out, and we pick up an integration constant, which is this eta, and that has a order 1 value. Basically, you're matching at the smallest wave number to have this pop out. And then this is the end result. So we have this in the blue box down here. This is the non-dimensional turbulent energy spectrum as a function of k. So what does this equation look like? So I'm showing this in the top right here. And so you can see we get something that looks more or less sort of like what we expect. So we have something that's peaked in the production range. In the intermediate range, we do get something that has the k to the minus 5/3 scaling, and then eventually we get something that dissipates and falls off. And in fact, according to the scaling approximation, you do get something where there is a maximum wave number, which I call k subscript c, where there is like an actual finite cutoff. So as I mentioned before, the fact that all these nonlinear states are sort of becoming normalized as you get to smaller and smaller k, eventually that nonlinear exchange, it essentially drops out, and that's where you have a finite cut. A little bit before that, which is the case sub nu, that's where viscosity starts to kick in and play an important role. So we can take this here and we look at the equation in blue again. And there's really only one fitting parameter here, which is this tau, okay? So when we look at experimental data, this is the same thing from before. We should be able to find the value for tau that puts the model curve through the data. And we see that a tau of about 10 to the minus 10, these numbers are very small, does in fact make the data go through. So just a quick note on what tau is. If you look back at the definition, this is essentially the ratio between the time scale for viscous diffusion across the domain itself compared to the time scale for like a characteristic fluctuation that's pushed along by the base flow. So you can imagine essentially the fact that this number is very small. What this means is that you have a very high Reynolds number turbulent flow. There's many fluctuations that can happen before viscosity would damp everything down. So you expect these numbers to be tiny. Okay. So one question I have here is you look at this thing, this equation, it doesn't look anything like a power law, but somehow you're still getting the scaling to pop out, right? And so why is that? So this is something that bothered me when I first saw it. So let's go back to Kolmogorov's picture. Okay, so he said that within this intermediate regime, we're far away from production and we're far away from dissipation. So we have this reduction, in terms of length scales. So according to the model, we only have two things. We have the wave number and we have the characteristic amplitude for this wave number. And since we've lost our details about like the domain geometry itself, we might as well not redimensionalize these and just call them k and u sub k. So let me now give you two pieces of information here. So if we go back to the model, okay, what we're looking for is a case where the production and the dissipation, which are these two terms, are approximately zero, and that's where you get this reduction of characteristic quantities. However, what we see according to the model is something a little different than what Kolmogorov said, and this is a very important subtle correction here. It is not that the production and dissipation are negligible. In fact, it's the sum of the two that's actually setting the scale for the differential equation. And there's a certain location within the intermediate regime where the amount of production is just canceling the amount of dissipation. Now, the absolute value of both of these things is very small. However, this cancellation is only exact at one point. But you can imagine, this cancellation is basically approximate over like a certain finite interval. And over that finite interval, that's really where you see this Kolmogorov scaling pop out. Okay, so that's number one. Number two, again, this is the definition from before with the energy dissipation. So without getting into the coefficients, I'll just give you two statements here which are equivalent. So one, according to the model, if the production and dissipation are exactly canceling each other, we can do the chain rule for this derivative with respect to k, and we get that the derivative of u with respect to k goes as u of k over k. Of course, as we look, these are the only two parameters we have, so this is how it has to work out. Equivalently, we can take number two and take its derivative with respect to k and say, okay, well, if this guy's about zero, then we get the same thing. So there's a difference in the coefficients, but I won't worry about that complication. So we can see that these statements are essentially equivalent, right? And this is from Kolmogorov's point of view where the scaling comes out. You have an essentially constant energy dissipation rate where energy is going from one length scale to another. But we see within the model, this is not because production and dissipation are negligible. It's because they're very small and they're canceling each other. So now we take the basic definition for the energy spectrum, which is this capital E sub k, which is the kinetic energy per unit k here, and we just plug in what we have up here for number two, and we get the Kolmogorov energy spectrum, and this guy out front is just some constant number. Okay.
Hey Justin, we have a question from the audience.
Yeah.
Is there a case where the Taylor approximation breaks down?
The Taylor approximation. Would the audience member mind explaining a little bit more? I want to make sure that I understand the person.
It's an anonymous attendee. If you guys want to follow up with another question or raise your hand, perhaps we can get you.
Yeah. So let me just say, for the Taylor approximation, are we referring to the sort of like frozen in turbulence that's like moving past a point? Is that what's meant here?
Okay.
Anyway, we can follow up in the discussion. I'll just make one comment. I don't know if this is addressing the question, but the general model framework does not make any assumptions about homogeneous isotropic turbulence, which is quite often a starting point. Here, when we do the scaling, that's where it becomes a little bit rougher, right? And there is some sort of a, sort of implicit assumption about homogeneity. However, it's a very weak approximation because we're going straight from the model and just doing the scaling from that. I should mention one more thing. So when it comes to the Kolmogorov spectrum here in the intermediate regime, the fact that this is coming about as this approximation, what this really means is that the scaling is never exact. It's really an approximation that arises by looking at a sort of asymptotic matching exercise between the production and dissipation. So you can think of it as there's really only two regimes. There's production and dissipation, and there's this very large overlap region between the two. And the intermediate asymptotics in that region gives you the Kolmogorov scale. Okay. Okay, so now, Varun, this is back to the question you asked before. Let's see how this actually works out in practice. So I've been working out a simple case here, which is turbulence in a cube with periodic boundary conditions. Oh, I think I skipped ahead. Here we go. So here, this is something simple enough that you can actually calculate it out analytically. So in this case, here's the setup. You have a cube, and within the cube, there's a simple shear flow, and that's given by the capital U here. You can see the capital U and the little case of U for the amplitude of the shearing. And I'm going to assume that for all the eigenstates of fluctuation I find, those themselves can be periodic within the domain. And so sort of physically, you can think of this as if we have a very, very large scale flow, like in the furthest right-hand picture. If you were to pick like a little small, like nearly differential element within here and zoom in, you can imagine that there's points where you have something that essentially look like the cube I have drawn here in the schematic. So here, we can first write down from this definition of U, what does the H matrix look like? And that's what's shown here. So we have the Laplacian operator, which is on the diagonal, and then the rate of strain tensor from U is appearing on these off-diagonal terms, okay? Now, what we want to do, just give you a quick roadmap, we want to find the eigenvalues that diagonalize this H matrix. Once we find those, then it's pretty straightforward to move forward and find these nonlinear exchanges. And then, well, there's the external fluxes, which are like a secondary form, so we're not going to worry about those. So again, this is what the full model framework looks like. We have all these U's that will be in one long column vector. The H matrix will be diagonal, and then we'll have these this anti-symmetric S operator. So first, let's do the linear part. And so here, we can find these by starting with an ansatz. So that's this U with the hat here. So we pick a certain wave vector. And so that will be in the argument. It can have a certain phase associated with it, and there's some constant vector out front. Now, the hat means that these guys are normalized. So if I take two of these guys, inner product, volume average the whole thing over the cube, I'll get a number that's either 0 or 1. Now, this guy, you basically plug it into here, and then you find the eigenvalues of that system, and here's what you find. You find that there's three different numbers out front, and so let me specify. You should expect to find an I equals 1, 2, and 3 because you have a 3 by 3 array. So you should for H. So you should be getting 3 eigenstates out of this. So what do these correspond to? So each one will have a certain wave vector associated with it. So these numbers here, the N, M, P, Q, R, S, are just integers, and that guarantees the periodicity. So each one of these have a little bit different form. You have eigenvalues here. So just to mention here, there's one that's well, they're all viscously damped in a sort of similar way. However, there's one where the base flow is essentially adding more suppression, and there's one where it's adding less suppression, right? So we have this difference on the base flow. And what this really corresponds to physically is that there's one eigenstate where the direction of it, it's vorticity, or line of vorticity is not being stretched, and in that case, it just kind of viscously compresses. There's one direction where the base flow itself is compressing the vorticity of the state, and that gives you the negative sign. And there's one where it's stretching the vorticity, and that's where you get something that can potentially be unstable here with the I3. The eigenvectors A, you can see what those are, and yeah, and then here's the vorticity vectors. Okay, so here, right? I mean, we have them, right? It's basically a bunch of sines and cosines, and you can add these up and put them in the array. A little bit more effort here. Don't dwell on this too long. I just want to emphasize that once you've found what these eigenstates are, you can go through and calculate all of these nonlinear terms. It turns out that what we find is a set of selection rules. And so I have these listed down here. Don't dwell on it too much. Basically, there's 6 kinds, depending on whether it's like a state 2 that's exchanging with a state 3, and the thing stretching it in the middle is a state 1 or 2 or something like that. I should mention, sorry, let me go back here. Yeah, so when we look at these states, there's something interesting, which is that they're all essentially 2-dimensional. So notice these wave numbers here, or these wave vectors, there's only 2 integer components in each one, right? So I give, a number m and a number n, and that specifies it. And then the eigenvectors themselves are, in a 2-dimensional plane. And this is true for all of them. So what we're seeing here is something pop out that's called Squires theorem. And this is a sort of famous theorem about turbulent instability, according to Navier-Stokes. And what he proved back in, I think it was like the 1930s, was that the most unstable wavelengths will always be ones that have a 2-dimensional coordinate dependence. And what we're seeing here is that, sort of what's sort of popped out automatically is that all of the eigenstates here, in fact, satisfy Squires theorem, which is kind of nice to see. Okay, okay, I'll skip over this. Now let's get to some comparisons. So first one is DNS studies of turbulence in a box. So DNS is direct numerical simulations. So first, let me explain. There's this one sort of famous paper from 2014. And they did DNS of turbulence in a cube with periodic boundary conditions, which is great, right? This is exactly the thing I just calculated. And so what they did here is they have this cube, and on the largest wavelengths of fluctuations that can happen in the cube, they basically have a sort of random arbitrary forcing on the largest scale. And then they watch the turbulence develop and cascade to all these smaller scales. So what you're seeing, okay, so the pictures here left is just a picture of the cube. One next to it is like a slice through the cube somewhere where you're seeing the vorticity, and basically it's turbulent is the point here. All the cubes have a characteristic length scale of L, and there's a certain metric that they can calculate to determine when there is the first statistical signature of this energy cascade beginning to develop within the box. Okay. And so what they do is they look throughout this whole box, and they calculate, find the average. They're sort of looking at every point within this this cube. What is the amplitude of the velocity gradients? Okay, so if there really isn't much of a connected cascade between different length scales, you'll expect all the amplitude of fluctuations will more or less be a Gaussian. And so what happens is that as you now increase the Reynolds number, you go from a sort of Gaussian probability distribution, which is what's shown on the bottom left plot, to when you start to have this nonlinear exchange and you really have a cascade, the tails of this Gaussian start to get thick. And that means that you now have energy that's transitioning from these larger length scales down to smaller ones, and they're starting to be affected. So that's what you see here, like the dotted line, the way they've plotted it with the log, that's a Gaussian, and then there's a certain Reynolds number where you start to see the tails getting thick. So what they were able to calculate looking at these probability distribution functions is as a function of Reynolds number. They can look at both the skewness and flatness of this distribution. And what you see is that there's a certain critical Reynolds number, which is equal to 158 plus or minus 28, and that just comes from distance between these data points here, according to this definition, where you start to see this statistical signature form, right? So this is just when the tails are getting flat. So we can put this in terms of the model that I've just showed you. So first, what does it mean when you start to see this cascade to larger k numbers? What it means is that you have a linear eigenstate that is destabilized. And so now its amplitude is growing, and the only way for it to maintain a finite value is to have a substantial amount of energy that's now being non-linearly exchanged into smaller length scales that are more viscously damped. So according to the model, we can take one of these H case of 3, and we look at, what's the largest wavelength that this guy would start to become unstable. So this would be the critical stability when it's equal to 0. And the largest wavelength is this case of 3 where the integers here are 1, 0, 1. So from here, comparing to what they did in the paper, there's a formal equivalency. So we take our capital U and our gradient, and the capital U corresponds to their random velocity fluctuations, and then the gradient is L, right? So the same as this L here. So you do that, plug it into here, it's just algebra, you rearrange it. When you find that according to our model, you get that the critical Reynolds number, where you start to see this statistical signature, is equal to 4 pi whole thing squared, which the nearest integer is 158. So not a bad comparison there. Okay, so let's do another one. There's another thing from experiment that is commonly measured in turbulent flows, and this comes from you take measurements of the turbulent energy spectrum. And when you take measurements of the turbulent energy spectrum, you can find the Kolmogorov scaling. So this is like the same sort of picture from before. And what you can do is experimentally find the value C, which is the proportional factor out front. And it's long been sort of postulated that this value C is a sort of universal constant when it comes to very high Reynolds number flows. So there's and essentially what this value C is, if you're on like a log-log plot, it's telling you, okay, you have the scaling k to the minus 5/3, and you're sort of shifting it up and down and finding where it intersects with the data. So there's a famous paper by Srinivasan from 1995 where he at the time took all of the experimental papers that had measured the C value. And so this is like atmospheric flows, oceanic flows, all kinds of things in the laboratory, shear flows, pipe flows, everything. And all of that is compiled onto one plot here. And what you see is that they find, taking all the data together, that C is about 1.59 plus or minus, a certain margin. So typically it said, C is about 1.5. That's sort of the rule of thumb. Now let's look according to our model. So here, previous from the scalings, we have our epsilon dot for the kinetic energy dissipation, and we have our version of the kinetic energy spectrum, corresponding to the Kolmogorov region. Now, so we start with those definitions, and we can now approach this from a different point of view. We can look at the turbulence in a box. And so here the idea is basically the following. If we have this box and it's a small portion of a very, very large turbulent flow, then we can do more or less a sort of unsolvable average over all the possibilities for a certain equilibrium configuration of fluctuations happening in this box, right? So you can imagine this is like the standard ergodic approximation in statistical mechanics. You say, well, over a long amount of time, if you have a chaotic system, it'll sort of visit every possible state. And so you sort of do an ensemble average over all those possibilities. So according to this turbulence in a box, we can do that. And so we take the nonlinear term here, and we do an ensemble average over all the phase combinations, as well as all the different selection rules for energy exchange. So it's a good amount of mathematics. Won't get into it, but at the end of the day, you find that you do get a number here. So you get a number that's times k u to the third. We look up at our definition here, and we see that this guy corresponds to y. And then when we plug into our spectrum here, this 1/2 y to the minus 2/3 is the C value. We find it's 1.523, which is, that's the solid line that I drew on this plot. Now, because I'm doing an ensemble average, I can also take the individual values that are like the highest and lowest that are, within that ensemble, and those correspond to these dotted lines here. And you see, for a sufficiently high Reynolds number, all the data is falling within there. So it's nice to see again, this is a kind of beautiful comparison. So that pretty much concludes the talk. the message here is that, we have a new mathematical framework, and basically the fun begins now, because now we can start exploring all these, different things and check off more boxes of these long-standing problems in the field. Just to give you a quick look ahead, this is all very preliminary, but based on this model, what I've also done is I've started a company. It's called ReynKo. You can guess where the name comes from. It's Reynolds and Kolmogorov stuck together. And we're basically taking this theoretical framework, and we're trying to go after all the problems that are touched by turbulent fluids. So the thing we're starting with right now is developing our own CFD program in-house that will have exact closure equations. We're at the very beginning. This is going to be a process over the next year or two to really get all this together. But I just want to mention, this is one result. I have one employee, Ian. He's our lead scientist, and he's been taking the equations for turbulence in a box and putting together a little code to actually simulate this. And so these are some of the very early preliminary results. And what you're seeing here is, you basically start the simulation, and these energy exchanges start happening. And each one of these curves represents the amplitude of one of these eigenstates. And at least at first glance, it looks like we are generating some kind of turbulence. So a lot more to come here, but I just want to give you an idea where we're going. And with that, I'll conclude. Thanks.
Thanks so much for the talk, Justin. This was really awesome. Some really great work you shared. If there's any audience questions, feel free to put them in the chat or the Q&A. Otherwise, I have a couple more. Okay, so let me go ahead and get started. So how do I understand sort of the advantage of this model over, something like DNS, with the spectral decomposition? Is this more sort of physical insight that we're getting out of your model? Are there some computational advantages? Yeah, anything you can share on that?
Yeah. So I guess first let me talk about DNS. So obviously DNS is more or less exact. So how do you do DNS? So for a particular turbulent flow, what you will do is say, okay, what's the minimum length scale of fluctuation before everything's like so viscously damped you basically don't care about it. And so that will set the size of your grid element when you discretize your computational grid. Now, even for like sort of modest Reynolds numbers, the number of grid elements can be massive, like well into the billions or more. And so it's really only like the simplest geometries that you can simulate that way, like namely turbulence in a box. Like you don't actually use this in practice when you're trying to like design and engineer a plane or something like that. Instead, what you have to do is you need to have a coarser grid. And as soon as you have a coarser grid, what this means is that there will be some length scale fluctuation where the flow is still turbulent, where you have to chop the energy spectrum. And from there down, you have to have some sort of analytical equation under a hood that is describing the turbulent behavior and how that interacts with the larger scale flow. And so that's really the thing that we're going after right now is, because we have these equations. So, I've given you one example, which is like the cube. So that's one example where if you have a cubic element, the equations will look more or less like that. This is giving you the exact representation of the turbulent state within that cube. And, the flux terms I didn't talk about, that sort of tells you how it will then interact with the larger scale flow. Now, so what we're doing is we're trying to build out from here, right? So obviously we're not going to, do a simulation of a Hilbert space for every grid element. That would be crazy. But what we can do is like some sort of clever approximations for what the energy spectra actually look like within the box coming from this model, and then we will be running those. So this is this would be a replacement for the sort of standard like K epsilon, K omega sort of models.
Right. Gotcha. And so how are you dealing with looking at like more complex geometries besides the box?
We haven't gotten there yet. Yeah, we're starting simple and then working out from there.
Gotcha.
Now, I will say, one of the things that's nice about the finite element framework is that there's a finite list of the kinds of volume shapes that you can have. So essentially what we're doing in the company is we're taking these different shapes, so rectangles, pyramids, and we're working out the equations exactly for those cases, and then we're going to figure out how to sort of simplify it to get something to run fast in the computer.
And so from a kind of like a commercial standpoint, are you guys kind of targeting on this kind of accuracy cost curve? Are you targeting sort of more accurate simulations? Are you targeting sort of cheaper simulations? I don't know if you've talked to folks in industry and this one sort of more desirable than the other.
Yeah. So short answer is both. I'd say most important is just accuracy and predictive power. Predictive power is really the big thing. So the way things are done now, like the current closure models that you use inside of a CFD program, I only learned this recently. I was listening to a seminar about turbulent CFD, and apparently you go into the program, there's a drop-down list of all these different subgrid scale turbulence models you can choose. And basically you take an educated guess and you pick one and you run a simulation and then you see how it looks. And if it doesn't look right, whatever equation you chose, there's some like empirical parameters in there, and you basically play with them until it matches some experiment data. So yeah, if what you want to simulate is something that you've already done the experiment for, yeah, you can get it to quote match perfectly. But I mean, this is really glorified curve fitting, right? This doesn't really give you predictive power when you actually want to design something. So I think that's really the biggest value add, is that when we get ours implemented, there will not be any curve fitting. It's just the one model you choose, and that should be like the best approximation that you can do within the simulation. Right. So accuracy and prediction, that's one. The other, when it comes to computational time, what I anticipate is that if you imagine like per numerical time step, using my model versus what we have now, given like the same geometry and grid size and discretization, it should be more or less the same. However, with that said, I do anticipate that in practice, you will get a significant speed up, because one of the issues with current CFD, and I'm speaking specifically about large eddy simulation, is that as the flow becomes more turbulent, you have to regrid the flow as you go to sort of get a certain handle on like these smaller and smaller length scales. In our case, since we're capturing the exact turbulent equation of state within the box, it does not matter how high the Reynolds number gets. So whatever grid discretization you start with, you can use that to run the whole simulation. So just the fact that you're not doing that, my understanding is that that's really where the biggest computational costs come from. You'll be able to save that way.
I'm curious if you've had any sort of pushback from practitioners who are maybe sort of steeped in their ways, not ready to.
Yeah, that's a whole. I could talk to you all day about stories on that front. Basically, what I found is the following. The people who are the most resistant are fluids engineers who have been like doing the typical CFD stuff for a long time. The people who tend to be the most enthusiastic are theoretical physicists who have the background to look through the math and say, yeah, this looked right, but have not personally worked on turbulence themselves.
Yeah, I mean, I saw a lot of the same stuff, using machine learning. I don't think industry is quite ready, but I think if you show the value,
Yeah.
Emil has a question. Keith, you might have to allow him to talk. I don't think I have that.
Let's see. Is it? Peter. Should I answer Peter's question?
Oh, I didn't even see that. Okay.
I see some in the chat. Oh, what about Matthew?
Yes. Okay.
Anyway, tell me what question I can answer.
I'll do the Q&A. Go ahead, Emil.
Hey, Justin, good to see you again.
Hey,
so just following up on this question about, the Taylor approximation. So you Taylor expanded something, I don't remember exactly what it was, in, delta K.
Yep.
Right. And you only kept the linear term, and there was some error with, K squared. So I imagine, there's some K value at which that, delta or K squared error becomes large. And, is there a case where, that happens before the viscous damping, takes over? Because, there's this energy cascade where at, viscous damping overcomes that.
Got it. Yes. That's a great question. So what this really comes down to is, you can imagine if you're at a certain wavelength of fluctuation, the series of approximation and how many terms you need to include is a measure of how far away does this particular K number interact with another one, right? So if it's like if there's like orders of magnitude where this one's still interacting with others, like significantly, right? So like they all interact, but it's really a question of order of magnitude, right? So like it's a dominant balance kind of thing. If you go far enough away and that's still significant interaction, then yeah, this Taylor series approximation can break down and it wouldn't be right. So there's sort of an implicit assumption here, which does have a more rigorous justification that there is a sort of finite length or distance away in K-space where the interactions are substantial, right? So the approximation is that the ones that are like, it's like dominant balance. So a certain distance away, like, yes, they're still in principle interacting, but it's not the leading order thing anymore. I mean, the thing that's really nice is that just taking the linear term, you get Kolmogorov scaling, and you get like this idea about the energy dissipation. So yeah, if you go to a higher order term, there's probably more interesting things that come out, but at least to this lowest order, then you're getting things that match what people measure and talk about.
And so this is where that value of like 3-ish came from, right? So it's like 3 wave numbers away.
Yeah. Right, exactly. And there, you have to really get into the details of what's the amplitude of change between this state and, k plus 1, k plus 2, k plus 3, k minus 1. And yeah, so it gets complicated, but overall, you kind of see that, yeah, this order 1 thing, looks about right.
Cool, thanks.
All right, we've got a question from Matthew. What applications look promising for ReynKo? How do you help companies understand the value this solution brings?
Yeah, good question. Yeah, so basically what we're doing now is we're looking at people who are doing engineering projects related to turbulent flows. So, really, I think the value now is we're looking for customers where the need to have like an accurate predictive design, adds a lot of immediate value. So I'll just give you, to give you a flavor of this, I'll just give you one example story. So Boeing, for instance, when they design a plane, from first sketch to first plane out the door, that whole development cycle takes about 10 years. And the total amount of money they spend is something on the order of like $30 billion. Now, it turns out that half of that entire budget and roughly half the time is spent building, testing, and refining physical prototypes in the wind tunnel. And the whole reason you have to do that is that you can't trust the software results, right? So this is the kind of thing we're talking about here is, if we really have something that's an accurate predictive software tool, then you can basically cannibalize that whole budget, right? So we're talking about building a plane for half the cost and half the time. And of course, you can imagine that there's plenty of other engineering applications where you would need the same sort of predictive software capabilities.
All right, we've got a question from Peter. Is the fundamental advance here eliminating the average versus fluctuations formulation, thereby avoiding the information destruction averaging entails?
Yes, that's exactly right. So sort of, fundamentally, like there's a like a fundamental theoretical problem, which is when you do that Reynolds decomposition, you run into the closure problem, and you no longer know what the relationship between these are, right? So basically, you're stuck, and this is what people have been doing for the last 150 years, is trying to MacGyver this extra equation together to get something that's solvable. So really, the advantage here is that by starting with a different decomposition, you can basically do a runaround and not run into that problem in a different framework, and then ultimately you may be able to, then do the time averaging and return to get something that does look like a sort of more standard closure equation.
All right, I think that's all the questions we have. Keith, I don't know if you have any, or we'll close this out.
Yeah, none specifically here, and I guess we can close off, with a few comments from you, Varun, in terms of where do you, so I guess you guys are two people who are sort of going from science into sort of industry, and sort of, I guess, any sort of experiences that you'd like to share, or things you've learned, or especially, I guess you guys have both worked on fluids as well, sort of what's missing in that space, and where do you think you're fitting in?
Yeah, I mean, I would say CFD in particular, I think it's a field that's kind of ready to be disrupted. I think most people would agree that kind of the field has been pretty stagnant over the last couple of decades. Software hasn't changed that much, algorithms haven't changed that much. We haven't really seen kind of anything revolutionary. I think the biggest innovations have kind of been like moving to SaaS products, like more cloud simulation. I think that it's done a lot for accessibility. But other than that, just taking advantage of like the increased computational power. I think the gold standard now is LES. This is more of a high fidelity simulation, but it's not something that you necessarily would have been able to do kind of 20 years ago. So end of the day, like the algorithms that we use today are still the ones that were developed like in the 80s and 90s. Just able to kind of do some more with them. So, anyone that can come in and kind of disrupt the industry with kind of a revolutionary new approach, I think there's a lot of potential for that, whether that's with AI or kind of what Justin's working on. I think there's a lot of interest in kind of breaking this plateau of innovation.
Yeah.
Okay. Go ahead.
Yeah, I'll just add a couple of things. So one is, when it comes to AI and fluid mechanics, there's two things that I see people doing. So one, there's a subfield where basically you're doing the machine learning in order to figure out what the closure equations are. Hopefully, optimistically, that will be moot with what we're doing, right? Because we've actually calculated this stuff analytically. The other part of it, however, is that, when it really comes to optimizing something, you may not have the time and resources to actually do the detailed fluid simulations all the way through, right? So if you have a sort of ground truth, like say with what we're doing here, you can then use those as the training data for a machine learning thing. And that would be like for a more specific task, right? Like optimizing like the shape of an airplane or something like that. And that's where I think machine learning will add a lot of value here.
Okay, thanks for that perspective. Thank you, Justin. Thank you, Varun. Just as an announcement, next week we have Ji who will be talking about dimensionality reduced encoded clusters with stratified sampling for robust training of machine learning interaction potentials. And with that, thank you and see you next week.
Cheers, guys.